Hi, I want to give you a quick overview of this new course on evaporites entitled Evaporite Brine and Sediment, a Salty Exploration. I, John Warren, have put this course together where I think it has a rather unique emphasis that you don't typically see in other programs and courses that discuss evaporites. It starts off with some very simple salty principles and builds a rich knowledge base from fundamentals in hydrology and hydrogeochemistry. The course starts out with the notion that evaporites are reactive. They're not carbonates. If we look at carbonate sediments, we see that the textures, the primary textures in carbonates, are typically associated with the biota that overprints and dominates primary textures. They're not siliciclastics, where primary textures that tend to indicate responses to varying physical energy levels in the environment. They don't show the same responses as siliciclastics in the subsurface, where subsurface diagenesis is typically a response to compaction. While in subsurface carbonates, they're certainly more reactive. Not as reactive as evaporites, but they're certainly more reactive, and they respond to changes in the geogenetic and the basinal fluid realms. Evaporites tend to be much more reactive throughout their time in the depositional setting, in the early and later burial, and in the uplift realm. They respond to both compaction and to fluid evolution throughout the time in the subsurface. And unlike other sediments, evaporites in the subsurface can flow. They can migrate, especially if they're halite-dominated successions. And we have a whole course on salt tectonics. In this course, I want to emphasize that in the subsurface, evaporites tend to dissolve like blocks of ice, and their most reactive areas, where we see the maximum change in chemistry and alteration in the evaporites, is around the salty edges. There is one overarching principle that evaporite sedimentology is driven by, and that is that evaporites are hydrogeochemical sediments. We have the hydrology in the depositional and the diagenetic realm driving the texturation, whereas brine geochemistry controls the depositional and diagenetic mineralogies. That means, and this is the whole premise of this course, if we understand the hydrological and the hydrogeochemical evolution throughout the rock and the brine's salty history at the surface and in the subsurface, then we'll understand in a much greater depth and predictive fashion the evaporite sedimentology. If we look at evaporites across time, what's important? We see that widespread evaporite depositional episodes are not equally spaced across Earth history. They are dominated by relatively unusual events where we see the appropriate conditions coming together on the Earth's surface, typically around plate edges, where we can form a massive salt system that can fill any or all of a very large proportion of marine-fed, hydrographically isolated basins in relatively short periods of time. The Messinian evaporites, some 1 kilometre plus thick succession of halite filling much of the deeper parts of the Mediterranean sump some 5.5 million years ago, was probably deposited in a few 100,000 years. We also see that throughout their textural and mineralogical evolution, evaporite sediments are labile. So their textures and their mineralogies, because they are so reactive, indicate the evolving hydrology and the evolving mineralogy in both their depositional setting and in their subsurface setting. So if we want to form a large mega evaporite, a mega halite or a mega sulfate basin in the ancient, like the Messinian, like the Permian evaporites in the North Sea, we need to have the appropriate grouping of plate tectonics, where we tend to see continent-continent proximity across a range of tectonic settings. We see those evaporite depositional systems located in the appropriate climate belt, typically associated with Hadley cells and in ancient greenhouse and hothouse earth climates. We'll discuss each of these topics in detail in the course. And we also see the appropriate drawn down, hydrographically isolated hydrology and the appropriate hydrogeochemical evolution tied back to the ambient marine chemistry. We'll look at evaporites from the Archean through to the present day and how the mineralogy has changed as oceanic chemistry and atmospheric chemistry has changed through time. Mega evaporite bodies are the result of the coming together of the appropriate hydrologic, tectonic, and climatic processes. It's why we see such a limited sampling in the Quaternary. We live in icehouse times, whereas 90% of the Earth's ancient history was in greenhouse or hothouse climatic mode, which favoured, along with the appropriate tectonic positions, more widespread deposition of evaporites over what were larger latitudinal belts. We also see that as marine hydrochemistry has evolved from the Archean to the present, evaporite mineralogy has also evolved. This course will emphasize all of these aspects, which were largely misunderstood because they've been interpreted as a variation on the carbonate and the siliciclastic, depositional and diagenetic themes. They are sediments in their own rights with their appropriate indications. So evaporites indicate, in terms of their primary textures, a varying combination of perennial subaqueous, ephemeral pan, or capillary evaporite settings. While in the subsurface, as the fluid chemistry evolves, evaporite textures and mineralogies evolve, and in some cases can flow into significant halokinetic structures. Throughout, we see an alteration of the original primary texture. In ancient evaporites, be they bedded or halokinetic, we see very little of that primary texture remaining. What we see is the textural response to that evolving subsurface hydrology. We can make a general observation that all evaporite textures indicate the hydrology and the hydrogeochemical conditions that were dominant at the time those textures formed. This is why evaporites can be quite misunderstood. A lot of undergraduate and graduate courses, as well as pages on the formation of saline sediments, they do recognise the importance of evaporites, but they tend to overlook or ignore the significance of the evolving hydrologies and the hydrogeochemistries. This course focuses in on those hydrologies and those hydrogeochemistries all the way from eogenesis through mesogenesis into telogenesis. Programs also fail to understand the specific skill sets needed to understand the rationale behind those fundamental controls and their outcomes, which is why there are modules devoted to both the hydrology of saline geosystems and to the geochemistry in those saline geosystems and how they evolve through time. So the aim is that as we progress through this course, we'll build up the understandings from the hydrological and hydrogeochemical fundamentals into a predictive capacity to recognise what you're dealing with when you're looking at salt-cored mega-evaporite settings across geological time. So what's in the course? Well, the course is some 20 hours in total, made up of a series of video chapters, about 60, which are between 15 and 30 minutes long. So they're short bites to allow you to integrate and understand the information in each video chapter. Throughout the course, you can talk to me while you're enrolled in the course. The enrollment period is 180 days, and I'm available for both online Zoom instruction or email. You also get a complete digital copy of my last book on evaporites, along with some relevant downloads of technical information and papers tied to the various topics. So within each video chapter, there will be a listing of references, fully referenced all that material that's in those chapters, and also there'll be a few PDFs to give you a little bit of additional background. On completion of the course, you get a certificate of completion. You'll also get a copy of my book. In terms of me, my expertise, I've got something like 30 plus years in applied and research experience in salty systems. I've written 4 major textbooks on evaporites, as well as many chapters on various aspects of evaporites, and I've published more than 60 refereed papers, and I write that monthly blog. You'll get a copy of this book, plus the expertise over those video chapters as you undertake this course. Well, I'm interested. What do I do next before I commit to paying to enroll for this course? Well, there are a number of things I suggest you do. I suggest you go to the course page via the Saltworks website and have a look at the curriculum. If you click on the different topics in the course curriculum, you'll see the range of topics that we cover in the various video chapters. Some of those chapters are free, and there's an eyeball symbol next to those chapters you can watch for free to give you a sense of the course's level and its content. There are free choices in most of the modules in the course. There's also a downloadable free course overview of PDF, which you can have a look at. There's also a walkthrough of how to use the course, so you can see the simplicity of the course and how you can address various topics. You don't need to undertake the topics in order. You can undertake them in an order that interests you and what you need to know about evaporites. Once you've completed the course, you can access that certificate of completion. If you do find this course appealing, then click on the enrolment button on the course webpage and it will take you to the payment page, and from there you can set up your account, and from there you can undertake the course. All the best. If you decide to take this course, I hope you find it useful, and I would appreciate feedback in terms of what you would like to be added to this course in terms of your interests.